want to learn about WebRTC through wide learning. So I want to know, I have a vague understanding, I want to know complete understanding of WebRTC and all the nuts and bolts. Let's use LLM to do some wide learning. Hi there, I'm an engineer. I have some idea of WebRTC, that it's a peer-to-peer protocol, nothing more than that. I would like to start with that until I know the nuts and bolts of WebRTC. Can we start?
Absolutely. Let's start with WebRTC. WebRTC stands for Web Real-Time Communication. It's a technology that allows real-time audio, video, and data communication between browsers and devices. It works peer-to-peer, meaning it connects users directly without needing an intermediary server for the media exchange. This is great for things like video calls, file sharing, and even gaming. Would you like to dive deeper?
What about streaming, live streaming? I thought that is a key use case.
Absolutely. Live streaming is a key use case for WebRTC. It allows for real-time audio and video communication directly between peers, which is perfect for live streaming events, video conferencing, and more. WebRTC handles the complexities of networking, like traversing firewalls and negotiating connections, making it easier for developers to implement live streaming features.
Okay, why not we use something like HLS, HTTP live streaming, where you watch on-demand video? Why not we use that? Why do we need WebRTC for live streaming?
Great question. HTTP live streaming, or HLS, works well for on-demand video but has higher latency, so it's less suited for real-time interaction.
What is the latency we are talking about when you say higher latency? HLS.
With HLS, latency can range from around 10 to 30 seconds, depending on the configuration.
I can have 6 seconds or 5 second media segment, right? So it's basically latency is the size of the segment, isn't it? Media segment.
Exactly. With HLS, latency is typically determined by the duration of the media segments and the number of segments the player buffers. Shorter segments can reduce latency.
What about LL, low latency HLS? What is
low latency HLS? Reduces the latency by using smaller segment sizes, often as short as 1 to 2 seconds.
Okay.
It also
so
includes features
the minimum you can do with HLS is a latency of 1 second, right? I got that. What about WebRTC latency? What are we talking about?
WebRTC typically offers latency measured in milliseconds, often around 100 to 500 milliseconds. This low latency is crucial for real-time communication and interactivity.
Okay, that's just an example based on the network condition. So it's basically in the order of millisecond. Is there any other technology other than WebRTC for this kind of low latency?
WebRTC is one of the few technologies that offers such low latency in the order of milliseconds for real-time communication. Other protocols or technologies might offer low latency, but WebRTC is particularly optimized for interactive applications like video conferencing, voice calls, and live streaming.
Okay, let's talk about live streaming. It's orthogonal to me. You said peer-to-peer without needing a server for exchange of media, but I'm assuming that there is a server needed for signaling. We'll come to that later. But it's orthogonal to me because let's say I'm live streaming. I have 300 participants in my live stream. Then how is it possible from my computer to exchange 300 streams can view from my computer? Is it possible? Is it peer-to-peer anymore?
No. For large-scale live streaming with many participants, a pure peer-to-peer approach isn't practical. In such cases, WebRTC often uses a server for media distribution. This can involve a selective forwarding unit, or SFU. which receives the media streams and selectively forwards them to other participants. This method reduces the load on the broadcaster's computer, making it feasible to stream to a large audience.
And what about other technologies other than SFView? Are there any others to forward?
Yes. Another technology is the media server, which can mix or transcode streams before sending them to the audience. This is known as an MCU, or multi-point control unit. MCUs can combine multiple video streams into a single layout, which is then sent to viewers. This is different from SFUs, which forward individual streams without mixing.
Okay, got it. Now we have, for high practical purposes, if I'm live streaming to more than a handful of audience, I need a MCU, SFU or MCU, is that right?
Exactly. For live streaming to a large audience, using an SFU or MCU is practical to handle the distribution of media streams efficiently, ensuring a smooth experience for the viewers.
Okay, so let's say, what is the recommended or prescribed number of users one can have without needing a server? 2, 3, how many?
In a pure peer-to-peer WebRTC setup, it's generally recommended to have no more than a handful of participants, typically around 2 to 5. Beyond that, managing the connections and bandwidth becomes challenging, and the quality of the call can degrade. For larger groups, using an SFU or MCU becomes necessary to handle the media stream.
Okay, go on.
So, with more participants, the network can become increasingly complex, and the quality can suffer due to limited bandwidth and processing power. SFUs and MCUs help manage this by acting as intermediaries, distributing or mixing the streams as needed.
Okay, fine, I got that. Now, I have questions about MCU and SFU later. I'll reserve for later. Let's start with how the signaling happens, and after that, exchange of audio and video happen. I would imagine that there is some kind of codec negotiation, like saying, okay, these are the codecs I have, and peer, what is your codec? For instance, I have H.264 and so forth, and I have an AAC for audio, and peer, what do you have? And this is my connection speed. I'm in a very good connection, and this is my bandwidth, network bandwidth, and bit rate. And I'm thinking I'm going to use audio and video. I'm assuming data, all three, let's say, using the data channel. So I use audio, video, and data, text. And then I am going to use, these are the codecs. And what else is needed in the signaling process?
Signaling in WebRTC involves more than just codec negotiation. Here's a breakdown. 1. Session description. Exchange descriptions containing media format information, like codecs. For example, H.264 AAC. Share IP addresses and ports for establishing connections. 3. Media capabilities. Determine supported media types and encryption methods. 4. Data channel setup. If needed, configure data channels for non-media data transfer. 5. ICE candidates. Exchange potential network paths using interactive connectivity establishment, ICE. The signaling process typically uses a separate server to exchange this information before the direct peer-to-peer connection is established.
Okay, so session description. So what are the protocols in signaling in, before actual video and audio flows through both the endpoints?
Signaling protocols commonly used in WebRTC include 1. Session Description Protocol, SDP, defines the media format, codec, and media transport information. 2. Interactive Connectivity Establishment, ICE, finds the best path for media between peers. 3. Session Traversal Utilities for NAT, STUN, discovers public IP addresses and ports. 4. Traversal using relays around NAT, TURN, relays media when direct connection fails. These protocols ensure that both peers agree.
Okay, turn is for if you're on VPN or something like that, right?
Turn servers are used when direct peer-to-peer connections can't be established, such as in restrictive networks or firewalls.
Okay, let's not worry about turn now. Now let's talk about SDP, ICE, and STUN. Talk about SDP, please.
SDP, or Session Description Protocol, is used to describe multimedia communication sessions. It contains information about media types, formats, transport protocols, and other parameters. SDP is used in the signaling process to negotiate and agree on the session details between peers, including codecs and encryption. It helps ensure that both parties can understand and process the media streams.
Okay, now where does ICE come into play now?
ICE, or Interactive Connectivity Establishment, comes into play to find the best path for peers to communicate directly. It gathers potential network paths, called candidates, and tests them to see which provides the best connection. ICE helps handle issues like NAT traversal and firewall restrictions, ensuring a reliable connection between peers.
Okay, so SDP comprises of maybe ICE candidates, and ICE candidates has STUN information. Is that right?
That's correct. SDP includes ICE candidates, which may contain STUN server information. STUN servers help discover the public IP addresses and ports, aiding in NAT traversal and establishing a direct connection between peers.
Okay, so let's talk about then from the bottommost, right? STUN. So I can give a bunch of STUN servers so that you can get the correct good path which has no congestion. Is that the idea?
Not exactly. STUN servers aren't used to measure congestion. Instead, they help in NAT traversal by discovering the public IP address and port of a device behind a NAT. Providing multiple STUN servers is mainly for redundancy and reliability, ensuring that at least one server is available to assist in establishing the connection.
I got it. So I give a STUN servers, list of STUN servers to determine the different IP addresses my endpoint has. Is that correct?
Yes, that's correct. The STUN servers help determine the public IP addresses and ports of your endpoint, which is essential for establishing direct peer-to-peer connections.
Okay, good. So STUN is clear. Now, how do we find the network path? Who finds the network path for these STUN servers? There are like five IP addresses, not STUN servers, 5 IP addresses determined using STUN. Now, how do I find the network path?
The process of finding the network path involves using ICE. Each peer gathers its local and relayed candidates, including those discovered through STUN. Then, the peers exchange these candidates via the signaling process. ICE agents on both ends perform connectivity checks to find the best path for communication.
Okay, so ICE is responsible, given the IP addresses, it will find. So, what is again reflexive candidate?
reflexive candidate is a type of ICE candidate that represents the public IP address and port as seen by a stun server.
Okay, what is the other thing which is seen by the turn server, like reflexive candidates?
The other type of candidate seen with stun is the host candidate,
No,
which
no.
represents the direct...
No. Turn, I said turn. What is it called? What is
the candidates gathered through a turn server are called relayed candidates. These are used.
Okay, relayed candidates. We're not going to talk about.
Isn't possible.
We're not going to talk about relayed candidates. Let's look at reflexive candidates. Are there any other candidates determined by stun?
Stun primarily helps discover server reflexive candidates. The other types of candidates are host candidates, which are gathered from the local network interfaces, and relayed candidates, which are provided by turn servers.
Okay, let's say we didn't provide turn server, so we gave a stun server. So you get two kinds of IP addresses. One is called the host candidate. These are candidate IPs, which is from the local network, and then reflexive candidates using the stun. Is that right? Is that right? So I get host candidates using local and reflexive candidates using stun. Right? Now
That's right.
These are IP addresses.
These come from the local device's network interfaces, while server reflexive candidates are obtained using stun.
These are simply IP addresses, correct?
Yes.
Let's say I'm a regular guy who's connected at my home using Comcast, right? Xfinity. How many typically candidates do we have? Reflexive candidates do we have typically in the United States?
Typically, there would be one server reflexive candidate for a home user in the United States using a typical internet service like Comcast. This candidate represents the public IP address and port assigned by the ISP, which is discovered through the stun server.
Okay, so let's say I'm talking about live streaming. Let's say people are doing that using either their home or home office, let's say, right? Now it should be one IP address, even though there could be potentially. Now, where else? Let's say I'm in the office, could I have more? I have like business internet and an enterprise network.
Yes. In a business or enterprise network, there could be multiple public IP addresses due to more complex network configurations. This could lead to multiple server reflexive candidates being discovered through stun, each corresponding to a different network path out of the enterprise network.
Okay, so how many could it be? Let's say I work for Google.com, right? Google company, right? Alphabet now, or Google. How many IP addresses would I have in terms of reflexive candidates?
In a large enterprise like Google, the number of server reflexive candidates can vary depending on the network's complexity and configuration. While it's hard to give an exact number, it's possible to have multiple candidates, each representing different network paths through various public IP addresses. These could range from just a few to several, depending on the network's architecture.
Okay, let's focus on just the home or home office case. I'm connected to Comcast. You said that there's only one reflexive. Maybe is there only one candidate or more than? Is there a local host candidate as well in this case?
In a home or home office setup with Comcast, you typically have both a host candidate and a server reflexive candidate. The host candidate comes from your local network interface, and the server reflexive candidate is obtained through the stun server.
Super, that's clear. Now let's talk about this. I'm going to establish, so I provide this SDPs, SDP. Give me a walkthrough of how this happens, this protocol dance happens, SDP protocol.
Sure, here's a quick walkthrough. First, one peer creates an SDP offer containing its media capabilities and ICE candidates. This offer is sent to the other peer via signaling. The receiving peer processes the offer, generates an SDP answer with its own capabilities and candidates, and sends it back. ICE candidates are exchanged, and connectivity checks are performed. Once the best path is found, media starts flowing directly between the peers.
Okay, so there's an offer and an answer. Basically, you have all of these media types, codecs, transport protocols, encryptions, ICE candidates, which has the host and the reflexive candidate in this case. Anything else is given the offer.
You've covered the basics well. The offer and answer may also include information about bandwidth limitations, session identifiers, and media direction attributes like send only, receive only, or send receive.
Okay, now I have a question. Let's say I am in the Bay Area. I'm streaming live from my home using. I'm in a Comcast network. Now I'm streaming. Let's say to two persons, right? But I want to avoid. There is a game going on in Santa Clara, which is a Super Bowl. Now, how do I avoid? If I know a priori that it's between 3 p.m. to 6 p.m., I'm going to stream right now, and my stream is going to last after 3 p.m. So I want to tell ICE saying, or in the SDP saying, hey, use this network path. How do I do that?
Unfortunately, you can't directly specify network paths in SDP or ICE. The best approach would be to use a turn server located outside the congested area. This way, your media traffic would be relayed through a more stable network path, avoiding local congestion.
No, turn is not an option. That might be too slow. So I don't need turn. So can I blacklist some stun servers and avoid this?
With WebRTC, you can't directly blacklist specific stun servers or network paths using SDP.
No. I just say that use these. I give a stun server list, right? Let's say list has 20. Can I say don't use this stun server in this region? Will it avoid the traffic? What is the deal?
You can't directly blacklist specific stun servers through standard WebRTC signaling. However, you can control the list of stun servers your application uses by excluding certain stun servers.
That's what I meant by blacklisting. Go on.
Got it. By controlling the list of stun servers used, you can influence which network paths are discovered. If you know certain paths will be congested, you can exclude those stun servers from your list, effectively blacklisting them to avoid certain routes.
Okay, let's take a detour of I provide a stun server list which excludes certain stun servers. How do I determine that beforehand? Like, how do I know a specific, this stun server is going to use a path via Santa Clara? Is there a way to determine that? My question is very simple.
Determining the specific network path a stun server will use can be complex. You could potentially use network measurement tools to trace routes and identify paths. However, in practice, this level of control is rarely feasible, especially for dynamic paths that may change due to network conditions.
Well, I can do this, right? I can run a probe from a traceroute probe from different location to a stun server, and then collect all the IP addresses and use some geo whatever API to find out what region. So then, or I just collect that, and then I could use that information to find out if, let's say, there is going to be Santa Clara, I can avoid these IP addresses, isn't it?
Yes, that's a doable approach. Running probes to trace paths and then using geolocation to map out the network regions can help you identify and avoid certain paths, like those.
Go on. Go on, please.
It's a more manual and proactive method, but it can give you control over which network paths to avoid based on your specific needs.
No, it's simple. I independently, there could be a system one could develop where I do a trace route across from different points to using a stun server to other different points. First, you select clearly what are the, in a particular region, what are the, where are the IP address peer. From there, I can send a trace route to different stun server and then collect all the IP addresses. If I did that, and I can, from now on, I can just have for this stun server, these are the paths. And then using geo IP, I can find what region to avoid and therefore what stun to avoid, correct?
That's exactly right. By mapping out the network paths for each stun server using trace routes, you can collect the IP addresses and determine which regions to avoid. This helps you selectively choose which stun servers to use based on your network requirements.
Okay, go on.
With this information, you can create a more informed stun server list, excluding those that route through regions you want to avoid. This allows you to manage network paths and improve the quality of your live streaming.
Okay, gotcha. How do I also determine to the IP addresses for me to run the probe? I can't do that from a server. It has to be an actual IP address of people residing. So how do I do that? Any ideas? How do I determine the different IP addresses, origin IP addresses? I can't. How do I build a list? How do I send a probe from there? Meaning, is it possible to find IP addresses and then stream from there, right? It seems to be impossible. Does it make sense? Can you respond? Okay, go on with what you know. Hello? Okay, I'm going to restart again. I'm trying to solve the problem of adding stun servers that avoid traffic where when a football game is going on, like a Super Bowl event is happening. How do I avoid the network path in the in my as an ICE candidate?
To avoid network paths that might be congested due to large events, like the Super Bowl, when using stun servers in ICE candidates, you can implement a few strategies. One is geographic filtering. Choose stun servers that are geographically distant from the event location. 2. Time-based rules. Implement rules to avoid certain paths during known high traffic times. 3. Dynamic path selection. Use real-time network performance data to dynamically choose the best paths. Would you like more details on any of these strategies?
Yeah, explode all of those three things. I'm interested in all three things.
Let's start with geographic filtering. You can configure the stun server to prioritize network paths that avoid areas with heavy traffic, like during a big event. This involves setting rules to exclude or deprioritize certain regions from being used as ICE candidates. Would you like to know how to set that up?
Yes, please.
To set up geographic filtering, you need to configure your stun server or your application's logic. Here's how. Identify regions to avoid. Determine which geographic areas you want to avoid due to potential network congestion. 2. Use GeoIP services. Implement a GeoIP service to identify the location of ICE candidates. 3. Configure stun server. Modify the stun server configuration to include rules that filter out candidates from the identified regions. 4. Implement in application logic. You can also add logic in your application to dynamically exclude certain regions based on real-time data. Would you like more details on any particular step?
Wait, so you're saying I have find a stun server, compose a list excluding those which are in the region where there is potentially high traffic. Is that what it is?
Exactly. You'd configure your stun server to prioritize or exclude certain geographic regions based on potential network traffic.
How do you do that?
To exclude stun servers in high traffic regions, follow these steps. 1. Collect stun servers. Gather a list of available stun servers. 2. GeoIP filtering. Use a GeoIP service to determine the geographic location of each server. 3. Exclude high traffic regions. Identify regions with potential high traffic, such as during major events. Remove servers located in these areas.
Okay, so all you're saying is find the IP address of the stun server and find which region it belongs to and exclude from the list. Is that what it is?
Exactly.
Okay, that's fine.
You'll
I
identify
understood.
the IP
I
addresses.
understood that. Now, let's say a game is going on, right? Later, right? And I am already using a stun server. Is there a way using WebRTC to change the stun server in flight during streaming?
It's not possible to change the stun server in flight during an active WebRTC connection. Once a connection is established, the ICE candidates are set, and changing the stun server would require renegotiating the connection.
Okay, so basically the connection will drop, a new connection will happen, isn't it?
Exactly. Changing the stun server in WebRTC would typically require renegotiating the connection, which could lead to a brief drop and a new connection being established.
Okay, so when it's simple, let's say I have a list of 60 stun servers before an event. I will just remove those stun servers based on the IP addresses. Their geo is going to be in that high traffic area, right?
Exactly. By preemptively removing stun servers located in high traffic areas based on their IP addresses, you can ensure that your WebRTC connections are less likely to be affected by network congestion during major events.
Okay.
This proactive approach helps maintain smoother communication.
Got
Would you
it.
like more details or assistance with
I got
anything?
it. I got it. I think it's very clear. Now, okay, that's a good approach. Now, let's move on to this problem. I'm in a mobile network. Initially, it's a great network, and suddenly the connectivity went. Or let's say I'm streaming from here, live streaming from home, but there are 4 other streams in my household, and therefore suddenly the network speed drops down, or neighbors are using it. I'm in Comcast, and then they're all streaming, and therefore my network conditions suddenly change. Now, how does WebRTC respond to this?
WebRTC is designed to adapt to changing network conditions. Here's how it responds. 1. Adaptive bitrate. WebRTC can dynamically adjust the video quality to match the available bandwidth, reducing the bitrate when the network slows down. 2. Congestion control. It employs algorithms to detect and react to network congestion, adjusting the data transmission rate accordingly. 3. Network handover. If possible, WebRTC can switch to a different network path or interface, like moving from Wi-Fi to mobile data. 4. Error resilience. WebRTC includes mechanisms to handle packet loss, ensuring that the stream remains as smooth as possible. Overall, WebRTC is quite robust in adapting to changing network conditions to maintain the best possible quality.
Give me a sentence for all of these 4 techniques, please.
WebRTC adapts to changing network conditions by adjusting video quality with adaptive bitrate, managing congestion through control algorithms, switching network paths when possible, and handling errors with resilience mechanisms.
Okay, got it. Now, tell me something. Talk about ABR, adaptive bitrate.
Adaptive bitrate, or ABR, is a technique used in streaming to adjust the quality of a video in real time based on the user's current network conditions. Here's how it works. If your connection is strong, ABR delivers high-quality video. If the network slows down, it reduces the video quality to prevent buffering. This way, you get smooth streaming, even when your connection fluctuates. It's a smart way to ensure a continuous experience without annoying pauses.
Okay, let's say I'm live streaming using to hundreds of people. I assume that I have a SFU or media server there. Now, tell me what are my options for ABR?
For adaptive bitrate streaming with your SFU or media server, you have a few options. 1. Server-side ABR. The server can monitor each user's network conditions and adjust the video quality it sends to them. 2. Client-side ABR. The client app can request different quality streams based on current network conditions. 3. Hybrid approach. Both server and client work together, with the server providing multiple quality options and the client choosing the best fit. Each method has its pros
Okay,
and
let's talk about client-side ABR. What are the techniques in client-side ABR?
Client-side adaptive bitrate techniques involve the following. 1. Buffer management. The client monitors the buffer level, and if it gets too low, it may request a lower quality stream to prevent buffering. 2. Network monitoring. It continuously checks the network speed and adjusts the stream quality to match the available bandwidth. 3. Heuristic algorithms. These algorithms make decisions on which quality to request based on past and present network conditions. 4. User preferences. The client may also allow the user to set preferences for quality or data usage and adapt accordingly. These techniques
Now,
work
what is the simulcast method of client-side ABR?
Simulcast is a method where the sender streams multiple versions of the same video at different qualities simultaneously. The receiver then selects the most appropriate quality stream based on current network conditions. This allows for more efficient bandwidth usage and a better viewing experience, as the receiver can seamlessly switch between streams without interrupting playback.
Okay, so simulcast is basically the peer will send 3 or 4 encoding bitrate, and then the client will choose which one, right?
Exactly.
Okay, then
With
if that's the
simulcast,
case,
the sender transmits multiple versions
is
of
there,
the video.
hold on, is there any other way other than simulcast for client-side ABR?
Yes. Another common method for client-side ABR is the use of adaptive streaming protocols like HTTP live streaming, HLS, or dynamic adaptive streaming over HTTP dash. These methods allow the client...
Wait, but I think HLS is out because I can't use it because the latency is, I want a very low latency, like milliseconds, right? I want like less than, like in the order of milliseconds. I can't use HLS, so go on.
For low latency scenarios, HLS might not be suitable due to its inherent delay. Instead, WebRTC is a better option.
No. In WebRTC, other than simulcast, what are the different client-side ABR approaches?
In WebRTC, Aside from simulcast, another approach for client-side adaptive bitrate is scalable video coding, or SVC. SVC encodes the video into multiple layers of quality, allowing the client to select the appropriate layer based on current network conditions. This method provides flexibility and efficient use of bandwidth, similar to simulcast, but with a different technical approach.
But which is compare both simulcast and SVC?
Sure, let's compare simulcast and scalable video coding, or SVC. Simulcast sends multiple streams of the same video at different qualities. The client chooses the best stream based on network conditions. It's simple and widely supported, but consumes more bandwidth. SVC encodes the video in layers, allowing the client to adapt by selecting layers based on available bandwidth. It's more bandwidth efficient and flexible, but can be more complex to implement and may have less support.
Okay, it is more efficient but complex to implement. Fine. But does all WebRTC endpoints support SVC?
No.
Okay,
Not
then
all
then
WebRTC
then
endpoints
what about
support
simulcast? Does it support? Is it supported by all?
Simulcast has broader support across WebRTC endpoints compared to SVC. While not universally available, it's more commonly implemented in modern WebRTC compatible browsers and clients. It's a more mature option.
Okay, fine. Let's say I do that. Now, what are the options in the server side for ABR?
On the server side for adaptive bitrate, or ABR, you have a couple of options. 1. Transcoding. The server dynamically transcodes the incoming video stream into multiple resolutions and bitrates. Clients can then request the version that best fits their current network conditions. 2. Stream switching. The server hosts pre-encoded versions of the video at various quality levels and switches between them based on client requests. Both methods aim to provide a smooth viewing experience by adapting the video quality to the viewer's network conditions.
Okay, now talk to me about the difference between transcoding and stream switching, because remember this in the context of live streaming using WebRTC.
In the context of live streaming with WebRTC, transcoding involves the server converting the live video into multiple qualities in real time, requiring significant processing power. This allows clients to request the quality that matches their network conditions. Stream switching relies on pre-encoded streams at various quality levels. The server switches between these streams based on client requests, which is less resource intensive, but may have limitations in flexibility.
When you say stream switching, this is are you talking about using, what do you call the first approach, the simulcast approach in the client?
No. Stream switching on the server side is different from the client-side simulcast approach. In stream switching, the server hosts multiple pre-encoded streams.
No. How does it host? It's a live stream.
In live streaming, stream switching involves the media server hosting multiple pre-encoded versions of the live stream at different bit rates and resolutions. Clients request the version that best fits their current...
You're not understanding. I have a stream coming in right now. It's not available. It reaches the media server. How will it be pre-encoded? It has to be transcoded to multiple bit rates, isn't it?
You're right. In a live streaming scenario, the media server typically transcodes the incoming live stream into multiple bit rates in real time. This way, it can offer various quality levels for client.
Okay, good. Now then, with that in mind, even stream switching you need to transcode at the server end, or it can use the switch based on the simulcast approach from the client. Then what is the difference between the transcoding and stream switching that you said?
The key difference is where the quality variations are generated. Transcoding. The server takes a single incoming stream and creates multiple quality versions in real time. This is resource intensive, but allows for adaptation to different network conditions. Stream switching. The server hosts multiple pre-encoded versions or uses client-side simulcast. The server switches between these streams.
Wait. Simulcast, I understand. We are specifically talking about live streaming. How does it otherwise have access to pre-encoded versions? Not possible. We are getting a fresh stream from the client. How is stream switching possible if I'm not doing a simulcast or transcoding?
You're right. In a live streaming context, without using simulcast, stream switching would require transcoding. The server must transcode the incoming live stream into multiple bit rates and resolutions to offer different quality levels. Clients can then switch between these transcoded streams based on network conditions.
Okay, now let's talk about how to instrument stream switching by looking at the bandwidth of the clients. Let's say this is a media server, it's a media server, or even an SFU, and I am going to stream switch, right? I'm transcoding multiple, or it could be simulcast as well. Somehow, how do I stream switch based on network conditions? Are there anything provided by either WebRTC or RTCP? What's the deal?
To handle stream switching based on network conditions in WebRTC, RTCP feedback. WebRTC uses RTCP for sending feedback about network conditions. The server can use this feedback to monitor client bandwidth, packet loss, and delay. Congestion control. WebRTC has built-in congestion control mechanisms that automatically adjust the bitrate based on network conditions. Server logic. The server can implement logic to switch streams based on RTCP feedback or its own assessments of the client's network conditions.
Okay, tell me, how do you do own assessment of network conditions?
To assess network conditions, you can monitor 1. Bandwidth estimation. Measure the available bandwidth by analyzing the rate of incoming and outgoing packets. 2. Packet loss. Track the percentage of lost packets, which indicates network congestion. 3. Round trip time. Measure the time it takes for a packet to travel to the destination and back, reflecting network latency. 4. Jitter. Analyze the variation in packet arrival times, which affects the smoothness of the stream. By combining these metrics, the server can make informed decisions about switching streams to maintain.
Got it. So it's basically packet loss, jitter, the usual suspects, and round trip time. And the new thing is bandwidth estimation. Is there any guidance for that?
Yes, for bandwidth estimation, WebRTC employs algorithms like Google's receiver estimation of sending rate, REM. This algorithm analyzes incoming RTP packets to gauge available bandwidth. It measures factors like arrival time and packet size to dynamically adjust the sending rate, allowing the server to optimize stream quality based on real-time network conditions.
Okay, what others are available for? I believe that Meta also has a machine learning based approach for bandwidth estimation.
Yes, Meta has developed a machine learning-based bandwidth estimation algorithm called BBR. It uses real-time data to predict network conditions and adjust bitrate accordingly, aiming for more efficient and stable connections. Other algorithms include Network Assisted Congestion Control, NACC, and Google's Congestion Control for Real-Time Communication, RCC, which also focus on optimizing bandwidth estimation for WebRTC.
Okay, are all of these open source?
Not all of these bandwidth estimation
No.
algorithms are
Specifically
open source.
that you mentioned. REMP, BBR, NAC, and RCC.
REM. This is part of the WebRTC standard and is open. BBR. Google's BBR is open source and available on platforms like GitHub. NACC. This is a proprietary algorithm developed by Meta and not open source. RCC. Google's congestion control algorithms for WebRTC are generally open source, but specific.
Yeah, go on. Go on about RCC.
Google's congestion control for WebRTC, often referred to as GCC, is a set of algorithms designed to optimize video and audio transmission over varying network conditions. While the specifics of RCC are not always fully open source, the broader GCC framework is documented and implemented in the WebRTC project, which is open source. Developments and enhancements.
But what do you mean by custom then? It's already implemented in WebRTC, right?
Yes, WebRTC includes built-in congestion control mechanisms.
Okay,
but
then
some-
we'll take that out of the picture. Whatever is not implemented, can we do REMP and BBR in the server that you're talking about?
Yes, you can implement both REM and BBR on the server side to manage bandwidth estimation.
Is it both by Google?
REM is a congestion control mechanism that's part of the WebRTC standard and has been implemented by Google.
What about BBR?
BBR was developed by Google as well. It's an open source congestion control algorithm designed to optimize bandwidth usage and minimize latency.
Okay, so basically the trick is that the WebRTC already has mechanisms like its own congestion control, RTP, RTCP feedback, etc. But we need to do our own bandwidth estimation, packet loss, round trip time, jitter, and that's how we can provide server side ABR. Is that right?
Exactly, you've got it. While WebRTC provides built-in mechanisms for congestion control and feedback, implementing your own bandwidth estimation using metrics like packet loss, round trip time, and jitter can help you fine-tune server-side ABR for optimal performance.
Okay, so let's say we instrument that. How do you make it available in the media server? See, I use my own bandwidth estimation algorithm, and based on which I can choose which So this is the stream switching, right? Let's do that, right? How do you provide? So let's say in the context of simulcast, all the producers or publishers are using OBS and using simulcast, and a stream comes in to the media server slash SFU. Walk me through how you can instrument our own bandwidth assessment estimation algorithm.
Absolutely. Here's how it works. 1. Collect metrics. The media server or SFU gathers real-time metrics like packet loss, round-trip time, and jitter from incoming streams. 2. Estimate bandwidth. It uses your custom algorithm to estimate available bandwidth based on these metrics. 3. Stream switching. Depending on the estimated bandwidth, the server switches to the appropriate quality stream variant provided by simulcast. 4. Adapt in real time. Continuously monitor network conditions and adjust stream quality as needed.
Now, doesn't WebRTC doesn't provide this automatic stream switching? Why should, or is it not fully effective?
WebRTC does provide automatic stream switching based on network conditions, but it may not always align perfectly with specific requirements. Custom bandwidth estimation allows fine-tuning, potentially improving quality and adapting to unique scenarios. It's a way to enhance control and efficiency in certain use cases.
Okay, let's say there is something called Red 5, right? Does it do this kind of server-side ABR?
Red 5 is a media server that supports various streaming protocols and formats. It can handle server-side ABR, including adaptive bitrate streaming, by providing multiple stream variants and switching based on client capabilities and network conditions. It's designed to be flexible and scalable for different streaming needs, including live streaming with low latency.
Okay, let's consider just the use case of live streaming. Does Red 5, does it transcode or just stream switches? Does Red 5 transcode as well, other than stream switching? Let me restart again. So the Red 5 media server, does it do transcode as well and stream switch, or in the context of server-side ABR?
Yes, the Red 5 media server can perform transcoding and stream switching, which is particularly useful for server-side adaptive bitrate streaming. This allows the server to adjust the quality of a video stream in real time based on the viewer's network conditions. Transcoding converts the original media into different formats or bit rates, while stream switching allows the server to switch between different quality streams based on the user's bandwidth and device capabilities.
Now, which is preferable? I want to have our own custom stream switching mechanism. Which is preferable? Is it preferable to use client side along with stream switching, or transcoding and stream switching, assuming I have good clients which has great connection and so forth? Let's say these are the hosts of multiple hosts of a live streaming event.
In a scenario with hosts having good connectivity and capable clients, client-side stream switching may be preferable. This approach leverages the client's ability to adapt to varying network conditions and doesn't require server resources for transcoding. However, server-side transcoding and stream switching offer centralized control and can ensure a consistent experience across different clients, especially valuable in live events. Ultimately, the choice depends on
Okay, let's say that client, I have a great host, they have great connection, that's a requirement, right? Now, is it any value in using Red 5 for stream switching?
If your hosts have great connections and can handle high-quality streams without issue, the value of using Red 5 for stream switching might be less about compensating for poor connections and more about providing flexibility.
No, let's say, okay, go on.
Sure, if your hosts have great connections and you're confident in the client's ability to manage streams, using Red 5 for stream switching might offer limited value. In that scenario, client-side stream management could be sufficient, as it reduces server load and potentially simplifies the setup. However,
Okay, let's say I have two types of participants. One is the hosts who have great network connection, another is a regular viewer, and everything is via WebRTC, and there is a media server in between. How do I need Red 5 here other than simulcast from the participants?
in this scenario, using Red 5 or a similar media server can be beneficial for a few reasons. Red 5 can handle the mixing and distribution of streams, which is especially useful for regular viewers with varying network conditions. It can transcode and adapt streams to different bit rates, ensuring a smoother experience for viewers with less reliable connections. Simulcast alone from participants can work, but it limits the ability to transcode or adjust streams dynamically. A media server like Red 5 can provide more control and flexibility in managing the quality and delivery of streams, making it a valuable addition to your setup.
Okay, let's say I am not transcoding at this server at all. And I have, like I said, I have a host with great connections. They're using simulcast. Give me a walkthrough of how server side ABR need not be Red 5. Our own custom bandwidth estimation algorithm will be helpful.
Sure. Let's walk through how server-side adaptive bitrate, streaming, ABR, can work with simulcasting and custom bandwidth estimation without using Red 5. 1. Host simulcasting. The hosts with great connections stream their video at multiple quality levels simultaneously using simulcast. Each stream is encoded at different bit rates. 2. Server receives streams. The media server receives all the streams from the hosts. 3. Bandwidth estimation. Your custom algorithm estimates the bandwidth and network conditions of each viewer. 4. Stream selection. Based on the bandwidth estimation, the server selects the appropriate quality stream for each viewer. 5. Stream switching. If the viewer's network conditions change, the server switches to a different quality stream in real time. This setup allows you to
Okay. Now, how will it work with SFU? Does this bandwidth estimation
SFU, or Selective Forwarding Unit, works by receiving media streams from multiple participants and then
How do this custom bandwidth estimation we talked about with a media server, can it work with SFU?
Yes, custom bandwidth estimation can work alongside an SFU. Here's how it can be integrated. 1. Bandwidth estimation. Your custom algorithm continuously measures each viewer's network conditions. 2. Quality selection. Based on the estimated bandwidth, the algorithm determines the appropriate quality level for each viewer. 3. Stream switching. The SFU switches streams according to the selected quality level, delivering the best possible quality for the viewer's connection. This approach can help optimize the viewing experience by adapting to varying network conditions in real time, even with an SFU in place.
So do you need a layer or a component after SFU?
Yes, typically, you'd have an additional layer or component after the SFU for managing custom bandwidth estimation and stream adaptation. Here's how it can work.
What about MCU, media server? Do we have to necessarily muck with it, or can we add a plugin or an external component is needed? What's the deal?
With an MCU, or multi-point control unit, the server mixes multiple streams into a single stream. This can add complexity to implementing custom bandwidth estimation.
Okay,
But it's
so let's leave out media server out of the picture. It's just SFU. SFU, what are the open source SFU and commercial SFU? Just give me the names.
Sure. For open source SFUs, you have options like Jitsi Video Bridge, Janus, and Medusa. For commercial SFUs, some names include Daily, Agora, and Wowza.
Okay, let's say the deployment has one of these SFUs. Now, what about Red5? Is it open source or what?
Red 5 is available in both open source and commercial versions. The open source edition provides core streaming functionality, while the commercial version offers additional features and support.
Can I fork Red 5 to add my own bandwidth as estimation algorithm?
Yes, you can fork the open source version of Red 5 and modify it to integrate your own bandwidth estimation algorithm. Keep in mind that you'll need to comply with the licensing terms of the open source project.
When you said Red 5, is it an SFU? Can it be used as an SFU?
Yes, Red 5 is primarily a media server, not an SFU. It's designed for streaming and supports various protocols, but it doesn't function as an SFU. SFUs are more specialized for handling real-time multi-party video conferencing by efficiently routing media streams.
Okay, then we need a component after SFU that could be open sourced from Red 5, provided the